While we go over multiple angle formulas, I'm going to show you each time we do a new set of formulas, we're going to do double angle formulas, and we're going to do power reducing formulas. We are not doing the half angle formulas that are included in the textbook. But each time we do a new set, I'm going to show you how we can derive those formulas from first the sum and difference formulas is how we can get our double angle formulas. And then we can get our power reducing formulas from our double angle formulas. Remember the day when we did the sum and difference formulas and I did that one proof on the board? Okay. So we can prove all of the sum and difference formulas if we wanted to. Okay, take the time to prove that these things work all the time. Okay. And then if we've proven that they work all the time, we can use them as we're going to in today to kind of generate the other formulas. Now, I'm not really going to ask you on homework and quizzes to generate those formulas, but it is a good thing for you to see, like, how are all these formulas, because you're going to get this long list, how are all of these formulas here? Like, how do we know them? Why do they work? That type of thing. So we're going to start with the double angle formulas. Okay, double angle formulas are derived from the sum and difference formulas from Tuesday. So those formulas that are on the front of your foldable are going to get us to our double angle formulas. In terms of the name double angle, okay, think about it like this. You might have a trig ratio like sine of x. That would maybe be what we could call a single angle. You just have x. Versus the sine of 2x, which we could say is the double angle. So you're taking the angle in the trig function, sine, cosine, or tangent, and you are doubling it in that formula. So we're going to write three formulas, more than three technically, but we're going to write three. One for sine, one for cosine, one for tangent. I'll actually have three for cosine. Okay, so we're going to start with sine of 2x, and I'm going to write sine of 2u, just like we did in our original formulas. Okay. Now, think back to sum and difference formulas. 2u would be the same thing as u plus u. Okay, so I'm going to write that out. The sine of 2u is really, with sum and difference, the sine of u plus u. Are you in agreement with me? Okay, if you look back at the foldable with the sum and difference, we could do the sine of u plus u. It tells us to take, if we're doing the sine of u plus v, to take the sine of u times the cosine of v. In this case, both of them are u's. So we would do sine of u times cosine of u, and then keep the sign plus. And then it tells us to do like the sine of v and the cosine of u, or cosine u sine v. Okay. So those are both going to be used for me. So cosine u, sine u. Okay, because my u and my v are both used now. Okay, u plus u. And what do you notice about those two terms? They're really the same. I mean, I have them written out of order, but commutative property for multiplication, it doesn't matter. So I can group them, and I can say that the sine of 2u is really 2 times the sine of u times the cosine of u. That's a double angle formula. So anytime I see sine of 2u, I can replace it with this formula, 2 sine u cosine u. Now, we'll just use the similar method for cosine. Cosine 2u is really cosine of u plus u. Go to your sum and difference formulas. For cosine, we do cosine u times cosine v, which in this case is another cosine u. And we always use the mismatching sign, so we're going to have a minus here. Sine u, sine v, or sorry, u, because v is u here. And how could we rewrite those? Cosine times cosine, u. Cosine squared u. Yeah, we could make this look a little bit nicer. So one of our cosine formulas is cosine of 2u is cosine squared u minus sine squared u. Now, think about in our previous sections, have you ever come across like a cosine squared x minus a sine squared x, and we would like plug in a Pythagorean identity, okay, at that point? Well, now we do have this piece here where we have like a cosine squared u minus sine squared u. We know that's equal to the double angle now, cosine 2u, but we didn't know that before. Okay, so we would continue to use the Pythagorean identity back in those sections. I am, though, going to use Pythagorean identities to write this two other ways. Okay, so this formula is acceptable. We can also say that the cosine of 2u is equal to the cosine squared u minus, and then insert your Pythagorean identity for sine squared u, which would be 1 minus cosine squared u. So because both of these are squared, cosine squared u, sine squared u, I could replace them with the Pythagorean identity. And what I like about that is I now have it all in terms of cosine squared. Okay. When I distribute the negative right here, it's going to be minus 1 and plus cosine squared u. So cosine of 2u is equal to 2 cosine squared u minus 1. And then we could repeat the process by replacing cosine squared with 1 minus sine squared. So I'll do that as well. On this one, I don't have to worry about distributing the negative. I'm just combining like terms. A negative sine squared minus sine squared is negative 2 sine squared. So cosine 2u is also equal to 1 minus 2 sine squared u. Okay. So these become ors. Now, you'll have to decide, like, which one do you want to use? It all depends on, do you want to have two separate trig functions? Do you want to have a sine squared and a cosine squared? Or do you want to have it all in cosines or all in sines? Are there any questions about what I have done so far? Yes, April.
When you replace the cosine squared u, wouldn't you have to distribute the 2?
What two?
Oh, okay, never mind. I get it. You're doing ors. Okay.
Okay. Anybody else have a question? Okay, so we have one more to go, tangent to u. Okay, one more to go. Tangent to u will be tangent u plus tangent u. Or not tangent u plus tangent u, tangent of u plus u. And then just like our warm-up, we're going to plug into the tangent formula for sum. Okay, so that would be tangent u plus tangent u in the numerator, all over 1 minus tangent u times tangent u in the denominator. And so our formula for tangent to u is 2 tangent u all over 1 minus tangent squared u. Okay, you can add the like terms in the numerator, and then in the denominator you can multiply to get tangent squared. These formulas, all 5 of them that we have for the double angles, will be included on your test that you're taking next Wednesday. So it's not that you have to memorize the formulas, it's that you have to be able to recognize which formula is going to be helpful to you, which one you would use, and then you've got to be able to execute that correctly. I cannot stress enough the importance of doing the daily homework so that you know if you're accurately using formulas. Let's do some examples then with the formulas. Okay, got all the formulas written down. It's the boxed formulas that we'll use for the double angles. Okay. My first example is solving an equation. Okay. And we'll solve this one in the interval from 0 to 2 pi, these are like the first problems on your homework. And so we'll set it up kind of like that. We'll only go within that one full revolution of the unit circle for our solutions. Okay, so we've got cosine 2x plus cosine x equals 0. And we want to solve that equation. Remember, to solve equations, your goal is to isolate trig functions. But we're going to have an issue here. Cosine 2x is not the same as cosine x. So they're not like terms. I can't combine them. And they're not something that I can factor. Like the cosine of a double angle is not the same as cosine squared. So we want to basically rewrite something so that it's solvable. Okay. So look back at all your formulas we just wrote down. What formulas are we going to be focused on? The cosine 2u's, right? The double angle for cosine. Which one of those will be most helpful for us in terms of solving? You say the second one. What does the second one say?
Cosine of 2u is 2 cosine squared plus 1.
2 cosine squared x plus 1. So we can change it now that we're working with 2x instead of 2u. We can change it into x. So we're replacing that double angle, cosine 2x, with cosine squared x plus 1. We still have plus cosine x. But think about what Emily did right there. She rewrote it so that we have still all cosines, but now we have a cosine and a cosine squared, which immediately you start thinking about factoring. Okay. I would rearrange my terms here so that I have 2 cosine squared x plus cosine x plus 1, and then factor that trinomial. So after Emily's step of replacing cosine 2x, the double angle, with one of those formulas, the formula that will be most helpful, this is now back to 5/3.
Who's correcting?
Yeah.
Which formula got the 2 cos squared x plus 1?
The cosine of 2x. So I said, look back at all your formulas. I'm going to go back to my slide. Which one of the formulas is going to be most helpful? Well, we've got sine 2u, we've got cosine 2u, and we've got tangent 2u. Obviously, we're looking at the cosines. And then we have 3 separate possibilities for cosine. So this is where you have to decide which one of those is going to be most helpful. Bless you. If I had, instead of a cosine x in that equation, if I had a sine x in that equation, I would use the last one of the cosine 2u's. But Emily chose the one with the 2 cosine squared so that we would be able to factor. That'll be 2 cosine x and cosine x. Good. Is this supposed to be minus 1?
Yeah.
Yes, it's a minus 1.
Okay, I remember.
Okay, change that. Good. I was like, this is not going to factor. Minus 1, minus 1. So I know my last terms have to be 1 and 1, but 1 is positive and 1 is negative to make that negative 1. So I just have to put the sign in the correct spot. In order to keep my middle term positive, I want my 2 cosine x to be positive. I want my 1 cosine x to be negative. And then I set my factors equal to 0 and solve. Okay, so if you had practiced 5-3 last Friday and this Monday, if you feel confident about solving through different methods, this is the same thing as that. We're just replacing with the double angle formulas at the very beginning. Trevor, can you give me some angles that have cosine of 1/2 between 0 and pi, or 2 pi? Pi/3. Do you know our second one? 5/3. Excellent. The quadrant 1 and quadrant 4 will have positive cosines. And David, can you tell me the cosine or the angle where cosine is equal to -1? Excellent, pi. And so you have your three solution. Now, if it didn't say from 0 to 2 pi, we would use the like plus 2 pi n for the complete solution. But the first examples in the homework assignment will say on the interval from 0 to 2 pi. So you only give those angles. Okay, another way we can use the double angle formulas is to rewrite or simplify some expressions. So we're going to rewrite 3 minus 6 sine squared x. And really the goal with these is for you to be thinking about and looking back at those formulas, like which formula does this look most like? How can I adjust it a little bit so that I can finally write it as one of my double angles? So look back at those 5 double angle formulas that I have. It doesn't look exactly like it, but which one does it look most like? A sine of 2u, a cosine of 2u, or a tangent of 2u? This looks most like cosine 2u, right? In all my choices, I have one double angle formula. Cosine 2u is 1 minus 2 sine 2u, sine squared u, sorry. Right? And so think about how can we change it so it looks like that. What do these two terms have in common? A 3, so factor that out. And then you can rewrite the 1 minus sine squared x as cosine 2x. So it's 3 cosine 2x. So this is really just kind of having you like look for similarities in the formulas, taking out that formula and then figuring out a way that you could then write it. And you might have to factor things or manipulate that a little bit. Here's another one similar to that. Rewrite 10 times sine of 2x cosine 2x. Okay, using the double angle formulas. So I want you to look back at the double angle formulas. You have 5 of them. Which one does it look most like? Sine 2u, cosine 2u, tangent 2u. This one looks most like sine 2u. Thank you, Mitchell. Sine 2u is supposed to be 2 sine u, cosine u. And so we're looking at the very front. It says 10 times. What are you going to have to do to change it? Factor out a 5. Don't just divide by 5 and make the 5 disappear, right? Factor out the 5. And there's also something, this one's an interesting one. There's also something a little bit different in the trig functions, right? In these trig functions, instead of being like sine x and cosine x, they're sine of 2x and cosine of 2x. So that means over here, our u was equal to 2x. So when you put u into the sine of 2 times u, it's really the sine of 4x. So you got to be on the lookout for things like that. Okay. Instead of expanding these with double angles, we're putting them back as the sine of 2u, but then u is 2x. So my final answer simplified would be 5 sine of 4x. And again, I think, you know, these problems are really just about looking for that pattern. What does it look like? And then understanding how the formula works, how that would have been my u, or that would have been my 2u, 4x, so that my u would then be 2x. Okay, if you had like sine of 3x and cosine of 3x, then your u would have been 3x, and the 2u would be 6x. So it goes back as a double. Are we okay with this? Okay, now we have another set of formulas. They are called power reducing formulas. So we're going to look at the power reducing formulas next. Power reducing formulas come mainly from the double angle formulas. So we got the double angle formulas from the sum and difference formulas. Now we can get something called power reducing formula from those double angle formulas. Okay, so in terms of power reducing, We're talking about things that have powers, things that have exponents. So it'd be like if you saw sine squared, you would reduce it so it doesn't have a square. So I'm just going to write no more squared. No more exponent, no more power other than 1. We'll look at what happens in the actual formulas and go back to that here in just a moment. Okay, so looking back at our double angle formulas, if you look at sine of 2u, that's not an incredibly helpful formula because it has no powers in it at all. 2 times sine u cosine u. Okay, so we're not going to use the sine of 2u. Cosine of 2u, we have 3 separate ways to write that, and that's going to be really helpful. There's 3 of them that we can choose from. We're going to choose the 2 where you either have cosine squared or you have sine squared if you don't have both. So that then we can reduce the cosine squared and we can reduce the sine squared. Okay. So let's start with those 2 formulas. Cosine 2u was equal to 2 cosine squared u minus 1. And we also have cosine 2u is equal to 1 minus 2 sine squared u. Okay. So, why am I choosing these problems? Because they have the power. Okay, they have cosine squared and they have sine squared. So, to create the power reducing formula, we are going to solve for the powered term. So like on that very first formula, I'm going to get cosine squared u all by itself. What will I have to do to both sides? Add 1, divide by 2. So this will turn into cosine squared u is equal to, it will be cosine 2u plus 1 divided by 2. I switched it around. That's your power reducing formula. Okay, for cosine squared. Over here we want to solve for sine squared, so we'll have a power reducing for sine squared. What will I have to do to solve for sine squared? Subtract the 1 and divide by negative 2, which is going to change the signs. The cosine 2u is going to be negative, the negative 1 is going to turn positive. So it's going to be sine squared u is equal to 1 minus cosine 2u all over 2. Okay, and so just looking at those 2 formulas, I think what's really interesting, if you go back up to this statement I made, when you do the power reducing formula for sine squared, it doesn't reduce it into sines. And even for cosine squared, it doesn't just reduce it into a cosine x. When you do the power reducing formulas, you reduce it into cosines of double angles. Okay, but you don't have the squared anymore. Okay, so that's a key piece. The last one we're going to do is tangent squared. And instead of using the tangent sum and difference, we're actually going to use the quotient identity. So if you remember back to 5.1, tangent squared as a quotient identity is really sine squared divided by cosine squared. And we know that sine squared is 1 minus cosine 2u all over 2. And if we were to divide by cosine squared, we would multiply by the reciprocal, 2 over cosine 2u plus 1. So I multiply by the reciprocal instead of dividing. And then the 2's cancel. And so our equation or our formula is tangent squared u is equal to 1 minus cosine 2u all over cosine 2u plus 1. Yes.
It just looks like conjugate, kind of like you can multiply the denominator by the conjugate to get a better denominator, something kind of like what we do in the.
Yes, you don't really need to, like there's not a rule about having the trig function in the denominator, so it's not like a huge issue. And the numerator is not the conjugate of the denominator, right? Because the conjugate of the denominator would be cosine 2u minus 1, which is not the same as the numerator. The 1 would be negative, the cosine would still be positive. Those signs are switched. You could multiply, this is going to be the power reducing formula for tangent that you would see in all textbooks. Okay, so of course we can manipulate that formula if we want to, but we just stop there. Okay. Are we okay on power reducing formulas so far? Okay, let's put them into use. We are going to rewrite the sine to the fourth x in terms of first powers of cosines of multiple angles. Ugh. That's the same directions you're going to see in the textbook, and same directions you would see on the test. So before we do the example, I just want to talk about, like, what does that mean, right? Okay. Rewrite sine to the fourth x. Okay, so I'm going to have sine to the fourth x. And I want it to have first powers, which means in my final answer, there should not be any raised to the fourth, squareds, anything other than raised to the first power, which we normally don't write. Also, we're putting it in cosines of multiple angles. So your answer is going to have a lot of like cosine of 2x or cosine of 4x or cosine of 6x. It just depends on what your u was, right? Going back to that one example where u was 2x, then we had 4x for our multiple angle. But again, put back to your different formulas for the power reducing. All of the formulas have that cosine of 2u. So that's that multiple angle for cosine. Just depends on what u was for, is it going to be 2x or 4x or 6x or 8x? And that type of thing. Okay, so did I give you a formula for sine to the fourth? No. What did I give you a formula for?
Sine squared.
Sine squared. How can you rewrite sine to the fourth so that it is sine squared? Sine squared squared, which means what? Sine squared times sine squared. So I would start by whatever I have there, rewriting it in powers that I have formulas for, which are squared. So sine squared times sine squared. Okay, I will give this to her tomorrow. She's at that little theater doing stuff. Thank you, guys. Okay, now use your power reducing formula. So you're looking back. Power reducing formula for sine squared is 1 minus cosine. This would be 2x all over 2, and then I would multiply it by itself. Like so. And now I actually have to multiply them out. I'm feeling good because I rewrote it, so now it doesn't have the raised to the fourth, it doesn't have the squares, but it does have cosines of multiple angles, so I like what I'm seeing so far. I need to multiply that out. So in the numerators, I'm going to have to FOIL, distribute, multiply. Okay. 1 minus 2 cosine squared, 1 minus 2 cosine 2x, and then it will be plus cosine squared 2x all over 4. And I'm kind of sad now, because what did I just do? I added a square. But I do have a power reducing formula. Okay, so now we got to use the power reducing formula again. Okay, so I'm going to keep my first two terms. 1 minus 2 cosine 2x plus, and then what is that power reducing formula for cosine squared 2x? Or 2u? Is cosine 2u plus 1, did you say? Over 2? Okay, so that's the formula that we're using. In this example where we have cosine squared 2x, what's u? Oh, I wrote this one. You were talking and then I was writing, and it was a bad choice on my part. That's the correct formula, right? Whew. Okay, what is u? The u is 2x. Okay. So when you put 2x in right there, what are you going to get? Cosine of 2 times 2x, which will be 4x. Okay, so you have to be careful on that second time. Whenever you do that second power reducing formula, because you had originally started to get those double angles for cosine, that means your u is that double angle 2x. So when you plug it into the formula again, it gets multiplied by 2. And we create the 4x. Okay, well, I'm feeling good because I got rid of the power again. So I like that. But I'm also still feeling a little sad because now I have this lonely fraction in the numerator of another fraction, and it looks funny. Okay. So here's a quick and easy way to simplify this. To get rid of this denominator of 2, I would really want to multiply it by 2. But I can't just multiply this one fraction by 2. I'd have to multiply the whole numerator by 2. And if I multiply the whole numerator by 2, then I also have to multiply the denominator by 2. So that I'm changing the way this thing looks, but I'm not changing what it really is. I'm multiplying by a well-chosen one for the whole thing. So I'm going to put a big parentheses around this. And then I'm going to say, multiply your numerator by 2, multiply your denominator by 2. So I'm really just multiplying by 1. And I have to distribute. 2 times 1 is 2. 2 times negative 2 cosine 2x is negative 4 cosine 2x. And then 2 times this fraction is going to cancel out the denominator. So I get plus cosine 4x plus 1. And in the denominator I get 8. You're almost done. By getting rid of that denominator, you now have like terms, 2 and 1. So the 2 can add with the 1 in the back. You should do that. And so I would write it as 3 minus 4 cosine 2x plus cosine 4x all over 8. They're in terms of cosines with multiple angles, 2x or 4x, but there is no more squares or exponents left in my problem other than 1. Yay! Now, side note, in the textbook, if you're checking your work tonight, they might factor out that 8 from the denominator as a 1/8. And write something like this. Okay. I don't care if you factor out the 1/8 or you leave it in the denominator. Either answer is acceptable to me. Okay. Any questions? Okay. Here is your homework assignment, and Chapter 5 test will be next Wednesday. all those formulas that we just went over are going to be provided to you. I'm gonna write up the first few problems so you can get started on some of them in class. We've got about 7 minutes or so before the bell rings. Okay, so I'll write up and you might be able to solve a couple of the first ones. They are equations, so they won't take